Hello, good evening everyone. Can you hear me? Hello, can you hear me? Okay, fine. Let us start. Actually, before moving to your resonance, let us start the discussion about the duality. Duality is nothing but parallelism between components or circuit variables or circuit itself. That is the parallelism. It represents the parallelism. Circuits are said to be duals of one another. That is, you have been given the two circuits and you can say whether they are dual of each other or not if they describe by the same characterizing equations. Same characterizing equations. Let us discuss with two circuit. Okay, and parallel connections. Okay, these are the two circuits. Let us write the characterizing equation for the both. For this I'll write the KVL. I'll be writing the KVL. So 1 upon C1 integration of I1 dt plus L1 di1 dt plus R1 I is equal to V1, right? So but I know that this integration of I1 dt is equal to Q1, the total charge. So represent this 1 upon C1 Q1 plus L1 di1, that is the di1 upon di1 upon dt. That is I1 is equal to, for this case I1 is equal to dq upon dt. So di1 upon dt will be the d square q1 upon dt, dt dt square. Similar, and r1 is equal to dq upon dt, dq upon dt, dq1 upon dt, which is equal to v1. So I want to rearrange it. So L1 d square q1 upon dt square plus r1 dq1 upon dt plus q1 upon c1 equal to v1. Let's say this is equation 1, governing equation to the series this circuit. Now I'll write the equation for this circuit. So you know that this for if I use a node equation here, I1 is equal to I2. I2 is equal to this current, let's say IR2, this current IC2, this current IL2. So what is this current? V2 upon R2. And whatever this current? C2 dV2 upon dt. What about this current? 1 upon L2, 1 upon L2 and integration of V2 dt. But we know that psi, that is sorry, V equal to d psi upon dt. Your I2 is equal to V2 is equal to d psi 2 upon V2 with d psi 2 upon dt, because I am writing all the that is subscript 2, so that's why I am using the psi 2, and 1 upon R2, then plus C2 dV2 upon dt, that is d square psi 2 upon dt square, then plus 1 upon L2 psi 2. Now rearrange it. So C2 d square psi 2 upon dt square, then plus 1 upon R2 d psi 2 upon dt plus 1 upon L2 psi 2 equal to I2. Now if you compare the equation 1 and 2, you see the characteristic equation looks similar, though they have different values. This is the second order linear differential equations. So there we can say that the circuit 1, this circuit 1 and circuit 2 are dual of each other. So you can collect the dual element or relate the dual elements. We'll move to the next page. Dual elements. You can easily see that dual element of, if you compare these two equations, you will find that dual of L is equal to C, dual of R is equal to 1 upon R, that is G conductance, dual of C1, the dual of C is equal to L, dual of C is equal to L. Same thing we have. So, and dual of V equal to I, dual of Q is equal to flux linkage. So we will write the dual. So dual resistance element, or can say, okay, or element variable, that is a physical variable, okay, or circuit. And dual, what is that? Dual, for example, dual of it, resistors, dual is conductance, that is G, right? Then inductance, inductors is the capacitors or capacitor inductor. Voltage is the dual of voltage is current, okay, voltage source, current source. Node, dual will be the mesh or loop. Series path, parallel path, okay. Open circuit, short circuit. KVL, dual is the KCL. Thevenin's Norton, right? Thevenin, then it is the Norton or Norton Thevenin. They are reciprocal, that is both way you can use, not the way that is a somebody asks you what is the dual of conductance, then it will be resistance. Then flux linkage, it is the charge, okay. So this is the dual. Suppose you want to they have been given a circuit. What actually dual represents is the same similar set of equation, but one cannot replace the other, understand, but you can have same similar type of response. For example, suppose you have been given an equation, differential equation, okay, you have been given the differential equation. Differential equation 1, another, because dual of the differential equation also another differential equation, just now we have seen in the previous page. Suppose this is the, let's say, response of this differential equation is the xt 1, or let's say c1 c2 e to the power minus t at, okay. Then if the dual of that network will have the same set of, let's say, x1t will be the c2 or c3 minus c4 e to the power minus bt. They see the similarity. They are not equal, but they represent similar equations. Okay, keep it in mind. If somebody asks you if the dual of a network has the same equation, no, you can easily say that it is similar equation. One cannot replace the other, but we can have a clue what will be the form of equation or form of solutions. How to draw the dual of a network? Sometimes it may appear. So how to draw the dual of a network? So I'll go by the example instead of going to literature. Find the dual of the network. Find dual of the network shown below. I'll go with the values. Okay. how easily you can convert into the dual network. Eight volt, 4 ohm, 6 ohm, 4 Henry, 4 farad. I have taken the small values, or you can say the that is integer value for the sake of understanding or edgeness of the problem. I need to find dual of this network. So first of all, you need to draw the circuit, because here is the question, so I need to again redraw it. Eight volt, 4 ohm, 6 ohm, 4 Henry, then 4 farad, 8 farad. The procedure of drawing the dual of the network is, okay, place the node in between node, single node, each loop. Place the node in each loop. Each individual loop you need to place a node. So here I put a node. Okay. Then here one node. 3 individual loop. So I put the 3 node and one datum or reference node. Here put one node in each loop and one node, datum node, outside the network. Now connect between all the nodes. Okay, connect between all the nodes, bisecting, or you can say, yeah, bisecting, or you can say intersecting, not each element once. For example, if I want to connect this element, that is this node and this node, only through one element at a time. Okay, then any other possibility? Yes, at a time one element. Okay, any other possibility with this node? From this node? No, we have exhausted all the element which would be possible to connect between the, let's say, node 1, 2, 3 and 0. So between 1 and 0 I can connect only two path. I can connect two path, each path passing only one element. So between 1 and 2 only one path, there is no other element. If there is an other element, you need to go through another time. And between 2 and 3, one element only. Somebody can ask me, sir, can I connect like this? No. Why? Because you are crossing or intersecting two elements. I have told you, you need to connect two between the each node, crossing or intersecting only one element. But you can very well connect like this, right? And there is no other way, so this one. Now doing this, now here replace it. Here is the node 1, node 2, node 3, datum node. Now connect the element, dual of that element between the that path, dual of element between this path. So 1 to 0, 8 volt. What will be the dual of voltage source? The current source of same value. 8 ampere. Now between 1 and 0, what is the next? 4 ohm. So what will be the dual of resistor? That will be conductor, or conduct resistance will be the conductance of 4 Siemens per, or 4 Siemens, 4 Siemens, or 1 upon 4 ohm. Four Siemens. And between 1 and 2, it is 4 farad. So 1 and 2, dual of 4 farad is the 4 Henry, because the capacitor's dual is the inductor. Between 2 and 3, 8 farad. So dual of capacitor inductor, 8 Henry. Clear? So now come to the 2 and 0. Between 2 and 0, only 6 ohm. So 1 by 6 ohm, or 6 Siemens, whatever you say, because dual of resistor is the conductor. Then 8 Henry, and next is the 3 to 0. 3 to 0, that is the 4 Henry. So that will be the 4 farad. Now we have drawn the dual of this circuit. Sorry. Hope it is clear. We'll move to the next. We'll move to the electrical resonance. Electrical resonance. So the electrical resonance occurs when total reactance is in the circuit reduced to 0. Electrical resonance, or we can say resonance, occurs in an electrical circuit resonance occurs in an electrical circuit when total reactance, or total reactance in the circuit reduced to 0. Reduced to 0. That means impedance is purely resistor. So resistor, that is your resonance occurs in a given frequency. When you vary the frequency or you reach at that frequency, right, your total impedance offered to the source is purely resistive, and at that time, whether it is a series resonance or parallel resonance, power delivery or power absorbed will be the maximum power will be delivered or absorbed by the resistor or source, resistor or load. Resonance is not limited to the electrical circuit. You can find the resonance in the mechanical circuit also. So designer always strive to avoid the resonance in a given system. You know, from the basic of control theory, when you reach the resonating circuit, the system will be, that is system response will be oscillatory, even diverging oscillation with the, there are also application of the resonance like in your oscillators or tuned circuit. We can use the resonance property to generate the in a given circuit, or you can amplifier can be generated in converted into the, if you connect the resonance circuit, your amplifier will be can be connected into the converted into the oscillators, or you can use it as a fire depending upon the which type of feedback you are using. Okay, let us move to the first, series resonance. Series resonance, you have a given circuit, series connection of R, L and C, and you connect a source. So I am writing everything RMS values, R, L and C, and this is your I, right? So you know the impedance offered by this is the R plus J omega L minus 1 upon omega C. I have told you that at resonance your total reactance offered to the offered by the load, or total resistance offered to, total reactance offered to source is 0. So total reactance is the omega L minus 1 upon omega C equal to 0. So omega equal to 1 upon LC root over. This is the resonance frequency omega n, which is 1 upon LC root over. At this frequency, this circuit will resonate, right? And you can easily see that Z is at that point, the magnitude of Z is the minimum. Voltage and current are in phase. So instead of remembering all these, just write a equation like this, short equation, and you deduce what many number of terms as you want. So my aim is, don't need not to mug up anything. For example, they ask you, this is the frequency axis, okay, that is the omega axis, here is the omega n. Now tell me, below omega n, whether it is a leading load or capacitive load, or below above omega n it is a load is the inductive or capacitive. You can easily say, and you know at omega n it is purely resistive, right? At omega n it is purely resistive. So if this is the value of R, so Z curve will be vary like this. Okay, I'll redraw again in the next page. We know that Z is equal to R plus J omega L minus 1. At omega n it is purely resistive. So if I draw the resistance line, so this is the resistance, and above omega n and below omega n Z increases, and here is the minimum point. This is the magnitude of Z. My question is, below omega n in this range, what is the Z characteristics of Z? Z is impedance is inductive or capacitive. See, capacitive impedance is like this. Let's say 5 minus Z2. This is a capacitive impedance. This is the capacitive impedance or leading load, we can say, impedance. And 5 plus J2, it is an inductive. That means inductor has the more impedance than the capacitors. So below omega n Z is capacitive. I leads B. Okay, and beyond omega n Z is inductive, and I lags V, and at omega n I and V are in same page. Here, now I will write all values, all voltages across the inductor, capacitor, and it is a very simple. You know the AC analysis. You should not have any problem. Vs. This is your I. R J omega L 1 upon J omega C. So I is equal to Vs upon R plus J omega L minus 1 upon omega C. Right? So at resonance, in general, first I'll write in general. It is in general. In general, at resonance. In general, I is equal to Vs upon Z, that is your, or you can write another one Z that is the impedance. Z is equal to R plus J omega L minus 1 upon omega C, and I is equal to I is equal to Vs upon Z, which is equal to Vs upon R plus J omega L. Okay, then your V, this is a VR. Okay, I will be marking as VR, VL and VC. That is the voltage across capacitors, VC, voltage across inductor VL, and voltage across the resistors is the R. So can anyone see the VR? VR is equal to R into I, and I put the value here. VL is equal to J omega L into I, and Vc equal to 1 upon J omega L into I. Okay, and they put these values also from I. Now what happened at the resonance? At resonance occurs, total reactance offered by the circuit is 0. So Z is equal to R. So let me change the color. So Z is equal to R. I is equal to Vs upon R. Let me know whether this is the minimum. Current is the maximum. Okay, and what is the VR? VR is equal to R into I. Same Vs. Then that, what does it mean then? Then the zero voltage for the inductor and zero voltage for capacitors. No, it is not the DC circuit. You will assume that zero voltage for, because they have voltage but they cancelled out. In fact, the maximum voltage also exists. And VL is equal to J omega L. I is the Vs upon R. Later on you will see it is the J Vs into Q. Many times it has been appeared in the GATE exam. At resonance, what is the magnitude of VL? That is the Q times Vs. Q is the quality factor of the resonance circuit. That is omega L upon R, where omega is the omega n. So I'll write the omega n here. At resonance frequency, so omega n. So Vs upon Q, where Q is the omega n L upon R, or same as the omega n RC. Later on we'll see how it is defined. Vc is equal to 1 upon J omega L into Vs upon R. Oh, sorry, that is the 1 upon omega RC. 1 upon omega RC, which is minus J Vs upon Q. Now you can easily see now Vc. So total voltage Vs is equal to Vr plus Vc plus VL. So Vr at resonance, Vr equal to Vs, and this is the Vc is equal to minus J Vsq, and VL is equal to J Vsq. So this cancel, and you only have the Vs at resonance. Right? So what you see here at resonance, VL and VC, the vectors at resonance, VL vector, VC vector is 0. What does it mean? The magnitude of VL is equal to magnitude of VC but phase of the VL is negative phase of the VC. Okay, so that's why they are getting cancelled. That means if one vector is this of length of A, another vector is of length of A but opposite direction, 180-degree opposite. This is also a MCQ point or MSQ point. Okay, that is 180-degree opposite. Now before moving to the power delivery, I will be correlating something so that you can easily find out the frequency lower cutoff lower what is that, lower frequency and high cutoff frequency, cutoff, yeah, half power, sorry, half power, or cutoff frequency also we told half power is the same cutoff frequency. Yeah, now for the time being consider, because I want to correlate, so I will be covering the what you study in the control system. Okay, I want to correlate the control theory you have studied with the network theory. Here, so let us say, just remember that whenever L you have in the frequency domain, in the Laplace domain, it is Ls. When C is there, then 1 upon Cs. R remains R. This is sufficient to analyze the circuit. Yeah, out of phase. Okay. Same it is, we are when we doing in the frequency domain, in place of S has a bigger scope in the S plane, we call it sigma plus j omega. That means all around this point. But when we restrict only on the j omega axis and sigma becomes 0, it is called the frequency response. Otherwise, it is a system response. Now with learning this, let us calculate for the series circuit. Right, R plus Cs Ls. So Is, that is current, Vs upon R plus 1 upon Cs plus Ls. So so what you will do here? So you will take common. Okay, first of all do the simplification. 1 upon Cs L Cs square plus R Cs plus 1, right? Now take common the LC. So 1 upon L into S square plus R by LS plus 1 upon LC. Okay. So now come to the this point, you will find the one critical resistance. Critical resistance, why I am telling it, because that has the significance. Okay, so critical resistance is defined as, first of all, you forget whatever in the numerator. So this is called the characteristic equations. Come to the characteristic equation. S square R upon Ls plus 1 upon Lc equal to 0. So roots of characteristic equation, you know, S is equal to minus R by L minus B minus R by L, okay, plus minus B square R by L square 4 LC root over. This is called the D, minus R by L plus minus D this square. Okay, this is the d root over. Okay, and this is called the, what is this d? D is called discriminant. Okay, that is your quadratic equation. So yeah, R by L na, yes, R by L. So discriminant d is equal to R by L square minus 4 into 1 by LC. Okay, 4 into 1 by LC. The critical resistance is found when we equate D equal to 0. When for critical R critical is found equating D to 0. So RCR upon L square is equal to 4 LC. So RCR L is equal to 2 LC root over. So R critical many times has come in the GATE exam, may not be these days, in the past. R critical is the 2 LC root over. 2 LC root over. Okay. Okay, we are not interested in the that denominator. Anyway, Harshad pointed out this is the 2. Okay, 2A, right. This is the critical resistance. What is the critical resistance value? 2 root over LC. Okay. Now I am going to define very important factor called the damping factor for the series circuit. Damping factor or damping ratio. Why it is called ratio, you could now understand. This is termed as a zeta. The zeta is equal to actual resistance in the circuit upon critical resistance for the circuit. So what is the actual resistance? R, and critical resistance just now we have found L by C. So half, so it will be R by 2 C upon L root over. R by 2 C upon L root over. This is called the your damping factor or damping ratio. It is the very important parameter in the designing of the control system in time domain or any domain. Zeta is the important parameters. And if you know the zeta, so quality factor is related to zeta, which is equal to 1 upon 2 zeta. Q equal to 1 upon 2 zeta. Okay. Another, if you have studied, we have done all these things, we will be going for the another parameter to define, that is called the damping constant of the, what is the damping constant? Damping constant is the real part of the real part of the real part of the you can say the solution, real part of the solution of the quadratic equation, or you can say the roots of the roots of the characteristic equations for this circuit only. Okay, for this RLC circuit we know that this is the characteristic equation, s square r upon ls plus 1 upon lc equal to 0. This is for the series RLC circuit. Okay, this is the characteristic equation. So damping constant, that is sigma, is the real part of the root of the characteristic equation. Obviously it will have a complex conjugate root. Okay, complex conjugate root, because the quadratic equation, otherwise if it is if the roots are, all the roots are real, so if all the roots are real, so there will be different roots. But when you have a quadratic equation, it should have all complex conjugate roots. So what is the real part of this? Real part of the root of the characteristic equation, that is, you can say that when you expand it, s equal to plus minus r by l, then the minus b plus minus b square r by l square minus 4lc root 2 over upon 2. Okay, and we are assuming that this is a complex, because if it is a pure quadratic equation means it should have a complex conjugate pole. Okay, that is the case of underdamped. So here this is the the magnitude of the real part of the root of characteristic equation. So this damping constant is the r upon 2l. When you divide, that is when I write r upon 2l plus r upon 2l square minus 1 upon lc root over. This part is a plus minus. This part is your damping constant, and time constant is the 1 upon damping constant, that is 2l upon r. Okay, with this now let us find out the maximum power, that is the maximum power. Obviously maximum power I have told you, the at resonance, what is the maximum power delivered to load or absorbed by the load, that is your E max at the resonance is your how much? At resonance Vs, that is Vr equal to Vs, that is source voltage. So you know the power absorbed by the load, that is V square by R, Vs square upon R. This is your maximum power. Yeah, because see, Hers, whenever you have a pure quadratic equations, obviously the roots will be the complex conjugate, pure quadratic. Otherwise, it will be factored into the two first order system, na? For example, s square plus s plus 1. This is a pure quadratic. You cannot factor into two first order system. But what about this? S square this looks like a pure quadratic, but it is not pure quadratic. It can be factored into the s plus 2 into s plus. But what about this? root 3. So this is the s plus 1 plus j root 3 by 2 into s plus 1 minus j root 3 by 2. यही है ना, equal to 0. Okay, this is the quadratic equation. This is, I mean, pure quadratic. This is also quadratic, but as per the, you are engineer here, you have already studied, it is not quadratic, it is the product of two first order system. But this is a second order, obviously it is a second order system, but it has two separable first order systems, but it cannot be separated in the there is a two first order systems. Okay, so control theory, we are more interested into the when the roots are complex conjugate. Okay, so let us move to the power calculations. So P max, or you can say P max, is equal to Vs square upon R. This is the P max for a series resonance circuit, because maximum power will be at the resonance. Clear? The magnitude of V square upon R, all these are RMS values. Okay. Now what is the half power? Obviously by P max upon 2, which is Vs magnitude square upon 2R. Now we need to find the frequency at which this occurs. Obviously you will equate with this power at the certain frequency. So what is the general current I? VR upon R plus J into omega L 1 upon omega C. Okay, so half there is a power in the resistor. Obviously power will be absorbed by the resistors. So P will be the I magnitude square into R, that is VR square into R upon R square plus J omega L minus 1 upon omega C square. Have I written anything wrong? Or V magnitude, V, yeah, Vs na, I equal to Vs. That's why I can check V square, and this half power, which is equal to the, see this is the general term, the power calculation for any resistors. So I need to equate it with the half power so that I can get the frequency. So equate it. So Vs square, V magnitude into R square plus omega L minus 1 upon omega C square, which is equal to half of this power, that is Vs magnitude square in upon 2R, half power. Okay, so now you can see, equate intuitively, you just see, that is your R. Okay, R upon R square plus omega L minus omega C square. See, Vs cancel, 1 upon 2R. Now see, intuitively see how you will be seeing it, equation, just without solving cross multiplication. Ultimately you will get the same result, but you see here, how can I get 1 upon 2R in the right side? how can I get 1 upon 2r? What are the possible ways I can get 1 upon 2r in the right side? Just check it. Here is the r square. Here is the r. Okay. Just think about this is 0. This is 1 upon r, but not 1 upon 2r. But how can I? If I see, for example, this way of thinking, r upon r square plus r square, r upon r square plus r square, it is exactly 1 upon 2r. See, that means my omega L minus 1 upon omega C square is equal to r square. What does it mean? That is magnitude of omega L upon omega C is equal to r. Magnitude, it can be positive, negative, so it can be positive, negative. So magnitude of omega L by this can be, see, omega L minus 1 upon omega C can be r or can be minus r. Both will satisfy this. So this is the half power condition. This is another question. See, lot of question. When you learn the concept, you will do the question. If you only learn the question, so that is a disastrous. See, half power occurs at what is the condition for the half power? That is, half power occurs when the magnitude of total reactance is equal to resistance of the circuit, resistance in the circuit. Magnitude of total reactance is equal to resistance. Half power occurs when magnitude of total reactance is equal to resistance. Resistance of the circuit. Yeah, resonance, there are a lot of questions. If the gate authority asks me to frame the question, then you won't be able to do the questions if you don't study the concept. Okay. So now the question is, find that frequency. Very simple, very simple. By magnitude, if this magnitude is equal to r, that's why you study the mathematics, algebra, linear algebra, complex algebra. Okay. By this, from this equation you can write omega L minus 1 upon omega C magnitude is equal to r. What does it indicate? Omega L minus 1 upon omega C equal to plus minus r. Simple. Right? So this is the omega square LC minus 1 equal to plus minus omega RC, right? Omega RC. So omega square LC plus minus omega RC minus 1 equal to 0. So omega square plus minus, just take out the LC common, R by L omega minus. Now I will draw the, how you remember. Do you want to do all this type of calculation in your GATE paper? Obviously not. Lot of reasoning or tricks. Now, that means we learn the basic and we are applying, relating. See, brain always map for the, your brain always map for the similarity to interconnect. The neurons in your brain, they interconnect in a predefined fashion so that you can recollect in the exam. Now you compare it with the characteristic equation of series RLC circuit. S square plus R by Ls plus 1 upon LC equal to 0. You see the some similarity, right? So if you understand this, if you correlate these, then you can easily write this equation directly. Another way also I will be directly, you can also remember the relations. So now the omega equal to R upon L, then plus minus B square R by L square plus 4LC root over upon 2A. Yes or no? Tell me. So plus minus R upon 2A. 2A means A is 1, 2 into 1. So 2L, then plus minus R upon 2L square plus 1 upon LC root over. Now I will write in short format. Okay, first of all, this is the negative frequency, cannot be possible. So you need to find one lower one. This is your omega n, and one lower one, that is omega 1, omega 2. So lower one, which one will be the lower one? This term is always greater than this, because this is the R upon L square is there plus 1 upon LC. This term is always greater than this. So I can write omega n is equal to minus R upon 2L plus R upon 2L square plus 1 upon LC root over. Obviously omega t will be the plus R upon 2L plus minus R upon 2L square upon 1 LC. This is the omega n and omega t. Okay, so I will shorten it. You study the damping constant sigma. So omega A1 is equal to minus sigma plus minus sigma square plus omega n square root over. Not plus minus na. Look. Okay, and omega 2 equal to sigma plus sigma square plus omega n. If you know this, then how to check whether it is correct or not? You know the bandwidth is always R by L. Okay, bandwidth. You can remember this R by L. So bandwidth is the omega 2 minus omega n. This cancel 2 sigma. 2 sigma, you see. What is the damping constant? R upon 2L. 2 into R upon 2L, which is R by L. Okay. Then product of that frequency, that is omega 2 into omega 1 is equal to omega n square. That should be, this is the property. This is the property. Now check here. Omega 1 into omega 2 is equal to minus sigma plus sigma square plus omega n square root over into sigma plus sigma square omega n square root over a plus b whole square, that is a square minus b square, sigma square plus omega n square minus sigma square. Sigma squares will got cancel, omega n square, correct? Right? So we think we learn each and everything. One thing is still left, that is the quality factor. Everybody remember the quality factor. What is the quality factor? What is the quality factors? How it is defined? Quality factor. The quality factor is defined as maximum reactive power in inductor or capacitor, maximum reactive power in inductor or capacitor upon maximum true power in where? True power in where? Resistor. Right? True power is resistor, reactive power in the inductor or capacitors. So this is the definitions. Okay. So that means at resonance. Obviously, maximum reactive power will occur only at resonance. Maximum true power will occur in the resistor. That will be occur in the resistance. Resonance. I mean, at resonance only maximum true power or maximum reactive power occurs because voltage maximum. So can anyone say what is the maximum reactive power? Q times. Yeah. So that is the byproduct result you are telling. Okay. By how much factor voltage and current amplified. Okay. So but this is the definitions. So maximum reactive power. Can anyone say maximum how you find the reactive power? Already I have told you, magnitude of I square into XL or magnitude of I square into XC, because current is the RMS value. So for capacitor I square XL, or sorry, for inductor I square, magnitude of I square XL, I square XC for the capacitor upon maximum true power in resistors. How much is the maximum true power? I square R. So I square XL cancel, XL upon R or XC upon R. What is the XL? Omega L upon R or 1 upon omega RC. This is the how we find the Q. Okay, Hers, clear everyone? Another definition is there. Q is the 2 pi maximum energy stored in inductor or capacitor upon maximum energy dissipated in one cycle. Same way you can find out these relations. Okay, so I'll be summarizing, right, for the series circuit. In the series circuit, your Z is equal to R, which is minimum. Current is equal to Vs upon R, maximum. Okay. Then omega n is equal to 1 upon LC root over. Then bandwidth, which is equal to R upon L. Omega 1 is equal to sigma square minus sigma square plus sigma square plus omega n square root over. Omega 2 is equal to plus sigma square omega n square root over. Write the sigma also. Sigma is equal to R upon 2L. Write the zeta also. Zeta is equal to R upon 2 C upon L root over. Anything we Q quality factor of series circuit is the omega L upon R. There is N. Okay, omega N 1 upon omega N R C. Okay, Now the see the भाई अरे यार बैंड पास फिल्टर तो यही है ना सी it is simple from filter response you see this is the omega n p max omega 1 this is the omega 2 oh I could not draw easily the distance same omega 2 this is the half power is the 1 upon root 2 in the voltage 1 upon root 2 point this is the 1 this is the half power so band pass easily you can see that it is a band pass filter the bandwidth is this from the response frequency response you can I use clear physical significance of the quality factor is the maximum energy inductor or capacitor can store okay an energy storing element upon the maximum energy dissipated that ratio that is called the quality factor because you know the quality factor and damping ratio are related to each other we have studied the dual yes or no we have studied the dual okay now you can apply the dual see the without knowing the without knowing the or you can learning the parallel resonance you can this is a series circuit parallel circuit by I mean that simple parallel circuit okay you can write all the terms this is not the time to ask what is the average quality factor okay so parallel circuit see the you apply the dual okay you apply the dual z is the here the minimum so z will be the maximum okay here is the minimum so z will be the maximum same r if it is r so z will be the r ir you mean say yeah ir will be the maximum then omega n same why I will prove it for dual of l is the c dual of c is the l so remains same see the bandwidth dual of r is equal to resistance is equal to conductance and dual of l is equal to c that is 1 upon rc omega 1 omega 2 same minus zeta square plus omega n square root over minus this is a plus na plus sigma square plus omega n square root over same this is a value here damping constant r z dual of r equal to z2 and l dual of l equal to c that is 1 upon 2 rc you can match and zeta of parallel circuit dual of r equal to z dual of c equal to l dual of l equal to c that is 1 upon 2r l by c root over quality factor of parallel circuit omega n remains same okay omega n remains same we have discussed before then l dual of l equal to c dual of r equal to z that is omega n r c or from this 1 upon omega n dual of r equal to g dual of c equal to l which is R upon omega n L. Okay, see the bandwidth and all these things we have derived. That means what does it mean? If you know only series, applying duality, you can get the all the result. Okay, in the next class we will discuss the how we got all, discuss the damping ratio, damping constant and zeta, qp, all these things, and omega 1, omega 2 will not discuss half power, but bandwidth also discuss all these things. And what is the value at the same, if you apply the even in the parallel circuit, here voltage is maximum, there the current will be maximum. Okay, in a series circuit we say that at resonance, that is capacitor voltage is the minus j q vs. Similarly, in the parallel circuit we can say the IC is equal to JQ supply, that is current magnification. Series circuit voltage magnifications, parallel circuit current magnifications. Okay, so a lot of things only you can improve with learning. There is no shortcut. Okay, shortcut you devise yourself. It suits you, then you can easily interconnect. Otherwise, you will learn the two set of equations. Till now you would be doing if you don't know duality. Okay. Okay, everyone, we'll see. We have almost stressed 1 hour 30 minutes, but I don't like. I like the class with some 1 hour. That is from 45 to 1 hour 55 minutes in between, so that you don't get bored. But these type of topics, when you start doing, start calculating, or start to know when the time